conseguem me ouvir? Acho que sim. Não.
Okay. Next speaker is Leonardo Prauchner from Universidade Federal do Rio Grande do Sul, Porto Alegre. Please, Prauchner.
Good morning, everyone. Thanks for coming to my talk. Before everything else, I'd like to thank the organizer and institution for this amazing opportunity to give my talk here. As mentioned before, my name is Leonardo Costa Prauchner. I'm a PhD candidate at the Universidade Federal do Rio Grande do Sul. My advisor is Sérgio Garcia Magalhães. But this work also has a collaboration of Elenir João Calegari from Universidade Federal de Santa Maria. And also I would like to thank you, Professor Peter Heisberg, for the discussions that allowed me to continue this work. So, as mentioned before, you are the professors. Well, before everything else, I'd like to make a little fun detail for everyone. That Brazil is a big, big country. The distance from Porto Alegre, which is where is our institution, and Natal is 4,000 kilometers, which is essentially the same distance if you drive from Portugal to Ukraine. So you can cross entire Europe, but you're not crossing the entire of Brazil because there's more Brazil to here. So it is a very big country, and probably one of most of you guys do not have the dimensions on your head about it. And also, I'd like to make an invite for if there's a future conference in Porto Alegre. We have an amazing landscape. We have this beautiful lagoon called Lagoa Lagoaíba, which you can see here in the sunset. Also, there's a view from the city from up, and you see all the lagoon. Here's the Universidade Federal do Rio Grande do Sul, and you guys have the Americans have all this big and incredible Central Park. We have the Park of Redemption, which is the Parque da Redenção. So feel welcome to come to Porto Alegre in the near future. Okay, so pretty straightforward. It's going to be motivation, model, method, results, perspectives, and conclusions. Nothing too fancy. Should be pretty straightforward. What is the main motivation of our work? Well, the Couperat's phase diagram has a very rich and full of phases. The phase diagram of it is complex, full of intricacies, details. But we are not able to look for every single detail, every single phase. You cannot consider everything in a reasonable humanly made work, right? But the main puzzle of the current landscape of physics is high temperature superconductivity. However, it is a very complicated subject. So instead of looking for the superconductivity and try to understand what is happening inside this dome, we're looking upwards in the charge order, which you do have. So what I'm trying to say is we're looking for the charge density wave phase while also looking for the pseudogap. There's a lot of discussion whether the pseudogap is a phase or a phenomenon. For this work, we are considering it is caused by the anti-ferromagnetic correlations and is not a phase, but rather an anomalous phenomenon. So the main focus of this work is to observe how those correlations responsible for the pseudogap affect the charge density wave phase and how they interplay together. What I'm trying to say is we're taking the correlations, put inside the charge density wave phase, and see what happens, right? So, but there's a problem with the pseudogap. As I mentioned before, there's a lot of discussion whether is it a phase or not. So we do not have an order parameter. How do we look into it? Well, we don't. We look for clues or everything else. This is the evolution of the Fermi surface. And we do have here 0.25 and 0.20 as a function of doping. There's a Lifshitz transition of the Fermi surface. And if we keep continuing raising the number of electrons, which means 1 minus doping, we get a Fermi pocket into the Fermi surface, which means there's one of our first clues. Before the pseudogap opens, we do have a Lifshitz transition. The pseudogap is also characterized by the suppression of states close to the Fermi level on the density of states. And this detail is going to be shown later, but I want you guys to keep track of this sign, almost like a red flag of the pseudogap trying to open. Well, and we have this theoretical phase diagram, which also, if you guys can see that in blue, we have a line of the Fermi surface. So before here's one topology, here's the other, and then there's the black line with the pseudogap. Again, almost like a sign that the pseudogap are trying to open. So that's the main landscape of our work. Now going for the model. As I mentioned before, we're trying to look for the what are those effects of the anti-ferromagnetic correlations in the charge density wave phase. So to do that, we're combining two approaches. We're looking for the Hubbard model for those correlations. However, obtaining a natural occurring charge density wave phase from it is kind of hard. So we're looking for a BCS, for the BCS-like model, which has a very well-defined and easy to obtain charge density wave order parameter. It is not a BCS model by itself. We're using a BCS-like approach for a model. So by combining both models, we have both an order parameter. The laser's not working. An order parameter and the correlations at the same time. So BCS-like model, then instead of looking for that superconductivity phase, you change the order parameter for the charge density wave one, which you consider that there's a nesting vector, and all the quantities that are generally well recognized, but for clarification reasons, chi k is the difference between the relationship dispersion and the chemical potential. Vk is our attractive interaction, the Perry mechanism, which is composed by an amplitude of potential, this cutoff factor, which is given here, that is obtained by simply saying, okay, we only care about the states close to the firm level. We don't need all of it. So we're cutting off the energy contribution close to firm level, and gamma k, which is the symmetry factor that I'm going to spoil the work for you guys. We're only looking for the D-wave symmetry because currently it is very well established that the charge density wave phase that is happening close to the pseudogap line is D-wave. And we're using a simple square lattice, and here's the order parameter, right? Okay, for the method, we're using the fermionic sum of, we're summing over the Matsubara fermionic frequencies method, so regular BCS treatment for the BCS-like model. However, if you take the equation of motion for the normal state, we obtain this very factor here, which is 1 over I omega n minus chi k, which is a simple Paul-Green's function, right? This simple Paul-Green's function, we can say it's just a G0, right? A simple Paul-Green's function, nothing special yet. And if we keep doing all the equation of motion, obtain this coefficient matrix, which is going to be relevant in a few seconds. So if we look for the main diagonal of that matrix, and we make all of those substitutions, taking care to correctly define all of the quantities, we obtain this new matrix. Then instead of having this chi k on the main diagonal and those variations, what we have is a main diagonal composed of those uncorrelated simple Paul-Green's functions. Okay, but where's the correlations? Well, from the Hubbard model that everyone is tired of hearing about it this week, so I'm going to glance over it. But for introducing the correlations, we have to treat the Hamiltonian. We look for the n-pole approximation, which has a very fun work of having this bend shift that carries those anti-ferromagnetic correlations. So by treating the Hubbard model through the n-pole approximation, we can introduce those anti-ferromagnetic correlations into the problem. So what we have is very well-defined order parameter, those anti-ferromagnetic correlations. We do have now a very well correlated Green's functions. And what we make, we look for that matrix, and we say, okay, that is a simple Paul-Green's functions. We can introduce correlations. It's fine. So we change those Green uncorrelated simple Paul-Green's functions for this Green function now correlated. And For the equation of motion, you just invert this new coefficient matrix, and you obtain the Green's functions matrix, and you look for the quantities of interest. And then after that, just was very well run-of-the-mill work, obtain the correlations functions by this. So we're looking for the density of states, the spectral function, and the order parameter using D-wave symmetry. And essentially, that's the method. That's our approach for this problem, right? Okay, for the results. When I told you guys before about looking for a Lifshitz transition, I'm looking for the spectral function. So we obtain the Fermi surface and those bands. So those bands are not obtained by just solving the determinant, looking for the poles. We're looking for the spectral function plotted onto all of these symmetry directions, high symmetry directions. And if you guys look, we have, yes, we have a competing topology here. It's not relevant because if you look for the bands, the high intensity values are in the nodal region. So what is saying? The anti-ferromagnetic correlations are more dominant inside this region, and we can say the charge density wave gap is in effect, as we do have a crossing of the band. But then we raise the number of electrons, we raise the occupation. Well, Lifshitz transition. And also, the high intensity of those bands are still in the same place. So that kind of gives us a clue of saying, okay, the anti-ferromagnetic correlations are in effect. They made this reconstructed Fermi surface suffer a Lifshitz transition. So what is the effect in the charge density wave phase? Now I just look for bands and Fermi surfaces. Well, by looking at the density of states, we can see that there's a suppression of states. I don't know if the orange line you guys from back of far can see, but it gets closer to the Fermi level, and there's a raise into the state. So that's a Van Hove singularity, which coincides with the Lifshitz transition opening for 0.9. And now if you look for the order parameter, there's almost what it's trying to say is we do have an optimal correlation regime because for 0.9 in U equals 16, so those parameters form the results before, we do have a rapid decay of the charge density wave order parameter, which means when that happens, they start competing with each other, and the phase abruptly ends. While yes, it's not a first order transition, it decays much faster than without those intense effects. And also, this also reflects on the specific heat that you can see for lower, not lower correlations, less intense correlations. Yes, the specific temperature decays. However, for U equals 16, which is the most intense regime, it decays much, much faster. So the conclusions is there's an optimal correlations regime which is enough to open those correlations, to be in effect, to favor the charge density wave phase, but not enough so that they can open the pseudogap. So while yes, we cannot still put our finger into the charge density wave phase or the superconducting phase and say, oh, hey, here's the pseudogap, we can take it. We do have a lot of clues that say, okay, those correlations, those effects are rippling inside those ordered states, and they can still be observed. And I hope this is a small contribution to trying to understand this puzzle, and for future perspectives to look for a more complete way, of course, include superconductivity, consider K-dependent hybridization, and look at the T-star line and the phase diagram of this completed work. And with that, I conclude with a picture of my institute, and thank you guys all for watching.
So, okay, questions?
So thank you for the nice talk. The charge density wave order parameter, the periodicity you use is commensurate, right?
Yes.
So if you have an incommensurate CDW phase parameter, you should also see the Lifshitz transition or not? Maybe things will go weird.
That is a good question.